Welcome to Worst Case Analysis using Mathematica. This is the third installment called KVL Solution. This is brought to you by Right Paradigm Consulting, and my name is Jay Oplinger. I'm the author. Last time we looked at these functions so you could understand basically what they do. So all we're going to do right now is just execute them by highlighting the right side and hitting Shift-Enter. That loads them into Mathematica. And we'll do that again for the other function. And now we will look at the circuit that we wish to solve. Notice that it's a relatively simple two-loop set of equations that we're going to generate. So let's write the equations for I1. We've noted that this is the direction for positive current in I1. So we start off with minus Vs plus I1 R1 plus I1 L1S because we're using the Laplace impedances. Then I1 minus I2 times R2. Then finally I1 minus I2 times 1 over C1S, again the Laplace impedance of that. So we'll execute that. Notice there's a semicolon so that we will not look at the output of this. Now the I2 equation, we start here going up through C1 and R2, and now I2 is in the positive direction. So it's I2 minus I1 times 1 over C1S plus I2 minus I1 times R2 plus L2 times I2 times S, Laplace impedance, and I2 R3. We're going to assume V out is across R3. So now we'll execute this. Okay, now the next step is we want to collect all the coefficients of I1 and I2. So we do this and also create two equations, EQ1 and EQ2. Remember our function is expecting EQ 1, 2, 3, etc., depending on how many equations you have. So here we'll just collect them using the Mathematica function collect, and we tell it what to collect, I1 and I2. So we'll execute that. And notice that it creates I1 here and I2 and minus Vs. And then for the I2 equation, we get a similar thing. Now we have everything we want in order to use our function. So we're going to enter those, and remember we only tell it what the list of variables are, in this case I1 and I2. So we hit Shift Enter, and now it returns us both the function, we have a semicolon here, so it returns us the values, but it also shows us what the matrix equation looks like. So we can use this to try and check ourselves. Notice the off-diagonal elements are mirror images of each other. Now, what we want to do is evaluate the value of I2. So we will do that. We'll call it small I2, so not to conflict with our original variable name. And we're going to do linear solve, which solves this matrix equation using M and Y. And we only want the second element because that's I2. So now we'll hit Shift Enter. And that gives us the equation for what the value of I2 is. Now we're assuming that V out is equal to I2 times R3. So we'll execute that. And again, that gives us an equation. And now H of S, or the transfer function, is V out over Vs. So we will execute that, and that gives us the transfer function that we're looking for. Now once you have the transfer function, then you need to do sensitivity analysis so that you can find out what the maximum deviation is from minimum to maximum for every component. So the first step in doing that is to find a list of the variables. So you can use Mathematica's internal function variables to provide that. And here's a list of all the variables. And now notice that S is in there because S is a variable. Now we're going to make up a variable table that we're going to use to replace the values. So these are the nominal values when you start a process. So R3 we're assuming is 1,000 ohms. C1 is a microfarad. R2 is 100. R1 is 5 ohms. L1 is 2 millihenries. L2 is 5 millihenries. And we just put S equals 1 because we're really not concerned with the variable S at this time. Now, once we have that, then what we're going to do is make a table of the list of each variable and then the derivative of this function here, h of s, with respect to each one of the variables separately. Then we will substitute in all the variables and numerically get a number. That's what the n is for. So once we have all that, we will have a list of the variables and what the sensitivity is. So let's take a look at what that table looks like. Now notice that some are positive and some are negative. So the way I treat this is, if it's positive, then we're going to set up the limits that go from low limit to high limit. If it's negative, we're going to set up the limits to go from high level to low value. So now we can adjust the table, take the variable table here and add in the tolerances. So here R3 is a positive number. So we enter in 1 minus, say 5%, and 1 plus 5%. And now here's one of the nice things about Mathematica is C1, most capacitors have a larger variation in tolerance one way as opposed to the other. So we have 1 plus, say 25%, and 1 minus 15%. Notice it goes the opposite direction from R3 because it's a negative number when we do the sensitivity analysis. And again, we follow through with each variable, putting that in there. And notice we eliminate the variable S because we know what S is. So let's execute that. And now what we wish to do is create a Bode plot of the function h of s. So to do that, I usually call it h j omega, which is h of s under the condition that s is replaced with I times 2 pi f, and it's also replaced with the variable table shown above. And then that gives us a numerical value for h of j omega. It actually gives us two, one for the maximum and one for the minimum. And notice their functions of frequency f. So now we normally make a Bode plot. We use a log linear plot of 20 log the absolute value of h of j omega. We're going to go from 50 hertz to a megahertz. And then we're going to put an axis label here just so we can see what this looks like. And we know what we're looking at when we do that. So here is the Bode plot. Notice here's the break frequency. And notice here it's decreasing by roughly 20 dBs per decade. Now, sometimes you might be interested in getting a time domain result. And in this case, we'll just assume that we have a step input. So to get the output, we multiply h of s times 1 over s, or the unit step. Again, replace the variable table with that. And now we're going to use Mathematica's power to do an inverse Laplace transform and give us the value of the voltage as a function of time. And notice it does it for both the minimum and maximum values. So let's plot those and take a look at them. We're going to plot them from 0 to about a half of a millisecond. And so notice here you can see here's the rising edge, and here's 1, which is where it should be. So there's a slight amount of overshoot due to that circuit. So we have gone through and we have looked at the basic steps involved in solving a two-loop equation and created the Bode plot for them and also the time domain plot. Next time what we're going to do is go back through this notebook and jazz it up by documenting it to create a real document out of it. So I look forward to seeing you next time.